So let's start. Good morning, good afternoon, and good evening to everyone. Welcome back. It's time to start our plenary session with our first invited plenary talk. And this session will take 30 minutes. It's 25-minute invited talk plus 5 minutes for questions. And to ask questions in a question session, I would like you to raise your hand first in Zoom and then unmute yourself. Alternatively, questions can be also asked on chat. I can read them to the speaker. And okay, I think it's time to start. It's a great pleasure to welcome and introduce our first speaker, Professor Chung-Pei Ma from Theoretical Astrophysics Center in Berkeley. And the title of her talk is Supermassive Black Holes in a Local Universe. Welcome, and I give the floor to you, Chung-Pei. Go ahead.
Thanks so much, Monika. Yeah, it's such a pleasure to join back in this time and to see all the progress and the excitement and the bright future. So today I would like to give just a little bit of an update on what we've been doing with dynamical measurements of supermassive black holes in the local universe in our efforts to both find new ones, uncover new populations, and in improving the dynamical mass measurements and the relevance to EHT and ngEHT. So I think it's good to start by just keeping a few things in mind about what we know and how we know about masses for the local supermassive black holes. So currently, there are 100-ish nearby galaxies have direct dynamical black hole measurements of the center. And by direct here, I mean using velocity information, kinematics, from luminous tracers. And currently, there are 4 types of mass tracers. The sort of bread and butter method using stars. Every galaxy has stars. Or ionized gas very close to the hole. Not all galaxies have gas emission, so that's limited to a certain type of galaxies. And masers, beautiful measurements, but again, far and few in between galaxies have masers at the center. An exciting new tracer, CO, there are a number of recent ALMA measurements of CO disks very close to the hole and using the disk kinematics to uncover the central black hole. Now, few systems have independent mass measurements from multiple tracers. So these tended to be just different galaxies. People are probing very actively using different tracers. And it's often very difficult to find sort of the few golden systems where you have multiple tracers available to compare. And we're working on that. And among the few ones that have multiple measurements of the same system, some agree in the famous first maser system by the CFA team and others, NGC 4258, the stellar dynamical measurement agrees very well with the masers measurement. On the other hand, famously, M87 has different gas versus stellar dynamical mass measurements. And as we have seen, the EHT black hole mass agrees with the stellar dynamical mass, but not from the ionized gas. And one last thing to just keep in mind is when we use stars as tracers, there's only one system in which we can use individual stellar orbits. Of course, that's our own galaxy. And only in our own galaxy do we have the luxury of resolving S2 and other stellar orbits to give us beautiful, precise measurements of the mass of the black hole. For all other galaxies, they're all too distant for us to resolve individual stars. So when I say stellar dynamical measurements, I'm referring to using integrated light, stellar light. We can't resolve individual stars, but collectively we can still use velocity distributions of the stars orbiting very close to the hole to infer its gravitational influence pull on the stars. Okay, so, and just to put the local dynamical measurements together to collect them, I just want to show the famous M sigma relation first pointed out in 20 years ago now. But there are various compilations of different measurements, but here's just one with some updates. And just to highlight that we are spanning 4.5 decks in black hole masses and plotted versus the host galaxy's sort of gravitational potential depth, the velocity, galaxy velocity dispersion sigma. And I've color coded and used symbols to indicate the 4 different tracers: stars, gas, masers, and excitingly, CO. And you can see M87 at the high end and Milky Ways at the low end here. Okay, and there's a lot of discussion, analysis, inference from the slope of this relationship, how we can learn from the slope and scatter about the feedback between black hole and host galaxy, about the symbiotic relationship between them. So it's a really, really active field of research. Simulators are trying to reproduce these relations. And so it's very important that we get more and more data and get better mass measurements. And another thing to stress here is these local dynamical direct measurements of black hole masses. They are the lowest or near the lowest rung of what I would call the black hole mass ladder here. And I just want to draw an analogy to the famous cosmic distance ladder, where you start from the local closest thing you can do, and then all higher rung, these methods all have to be calibrated to the lower rung. So these famous Cepheids, for example, TRGB stars, the recent debate about the Hubble constant, they all have to be calibrated to lower measurements, the method at the lower rung. So similarly for black holes, we hear a lot about AGNs, quasars, massive galaxies at high redshift hosting supermassive black holes powered by them. These methods, for example, reverberation mapping for AGNs, or these broad emission line width, we use that to infer sort of indirectly the black hole's mass. All those methods have a coefficient that's unknown, the virial coefficient, for example, that must be calibrated to the direct measurement I just showed you. So you need to find a system for which you can use both methods. So the stellar and the gas dynamics that I showed in the previous slide have been the sort of the very important local relation that we need to pin down. Then, of course, very excitingly, for 2 galaxies now, the Milky Way, we can use S2. And then, of course, now with the ngEHT, we have the method of direct imaging for M87. Okay, so so getting the lowest rung accurate and precise is incredibly important for all the inferences we're going to make about cosmological black hole growth and galaxy growth and evolution. So I would like to just highlight sort of 2 + 1, 3 areas very quickly of some recent progress we're working on in improving, advancing the stellar dynamical measurement part of black hole masses. Okay, so first I just highlight some new observations we've been obtaining. So I want to emphasize, focus on the massive end, because that's relevant for eHT and ngEHT. How many more M87s are out there? So these big black holes, you would have thought they have larger event horizon, they have larger gravitational sphere of influence, so they should be easier to find. But a major challenge had been that the central surface brightness of the stars, of the galaxy, is extremely faint. So here I'm showing just a collection of elliptical galaxies, HST imaging data for the surface brightness density as a function of the radius from the center of a galaxy to the outskirt. And these blue ones are just run-of-the-mill elliptical galaxies with this sort of Vogelor Sirsic profile. But I'm highlighting some of the black hole galaxies hosting some of the largest known black holes. You can see M87 starts to flatten, and the few we have been monitoring that we found bigger black holes than 6 billion solar masses have even lower surface brightness. So there's a lack of deficit of stars at the center. So observationally, it makes it very, very difficult to get stellar absorption line spectra to measure the velocity distributions to get the black hole mass, to detect the black hole. So the Hubble, which we have been used to detect a lot of those sources I show on the M-sigma relation, really is too small for high signal to noise spectroscopy. So our team had been pursuing these bigger black holes on two fronts. One is the massive survey that we've been doing since for the past 6-7 years now, is we systematically target the 100 most massive elliptical galaxies within the distance Chung-Pei Ma cluster, and most massive by stellar mass. So this is a well-sampled homogeneous sample for which we would like to understand the galaxy evolution, including the black hole. We want to find the black holes at the center, and only a handful of them had previously detected black hole masses. And we're also now moving beyond massive to do the extended massive, to go beyond the volume of 100 megaparsecs. And at that distance, the Gemini McDonald integral field spectrographs, which we relied on, are not sensitive enough to detect these very, very faint cores. So fortunately, Keck has a new integral field spectrograph that came online a few years ago called KCWI. And we have been using that extensively to move beyond 100 megaparsecs. But each measurement takes a lot of effort, data sets, and extensive orbit modeling I'll speak about a little bit. Okay, so just very quickly, this is just showcase the power of integral field spectrograph. That's a workhorse for us on these big telescopes. So basically, in one exposure, we are able to get stellar spectra at 2D, XY of the galaxy. So unlike the traditional long slit, for which you can only get the major axis or some axis to get the spectrum, here we have a 2D coverage of what the stars are doing. And we have a spectrum, so it's called the data cube in the third dimension. And here I'm just highlighting two examples. One is the central part of this galaxy. This is from Keck KCWI. And you can see these absorption features well known for elliptical galaxies, calcium H and K, H beta, magnesium B, and so on. And even the faint outer part here, this spectrograph is so sensitive that we can bin together some spaxels to get very high signal to noise spectra. And we use the width of these absorption lines to see how they're broadened compared to template stars to measure the velocity distribution of stars I spoke about earlier. So we don't have individual stellar orbits, but we can get this F of V or L of V and mapped around the whole galaxy. So, and importantly here, we're not just getting the radial velocity, blue redshift, or just the velocity dispersion, the second moment of this velocity distribution. Rather, we get the skewness, the cortosis, the higher moments. That we want to map out the entire stellar velocity distribution and many, many parts of the galaxy for which we can tease out the influence of the black hole on these stars through short orbit modeling. Okay, so it's a very involved process to measure one black hole mass. And we really want to get these higher moments, velocity moments measured accurately. And that's why we need signal to noise of about 100 or higher. And that's why we need such big telescopes and sensitive spectrographs. So I just want to highlight one result. And here I'm only showing the second moments, which everyone likes to see, the sigma, right? Velocity dispersion of the stars. And here I'm just showing 20 massive galaxies that we probed using two spectrographs here. And each one is just a velocity dispersion as a function of radius from the center of each galaxy. But since we have azimuthal coverage, right, we got all 2D information at a given radius, you are seeing many azimuthal bins. And here I just want to show that these are 20 massive elliptical galaxies, and sigma is not isothermal, right? You see intricate profiles dropping. And in this case, 4874, the lower right corner, this is a giant coma galaxy. You can see the velocity dispersion rising rapidly, perhaps due to the dark matter, right? So there's a wealth of information embedded in not just the second moments. We have these plots for all these moments. And all this information goes into our orbit modeling. But very strikingly here is the magenta, which is the Gemini GMOS IFU, for which we get a very central part of what the stars are doing. You see the sigma growing. And usually this is a telltale sign of a black hole at the center. Okay, so we're working on all these galaxies and trying to get the black hole masses, and we're reporting one by one. And just to one slide about beyond massive. So that relies on Keck KCWI. And here I want to come back to the surface brightness distribution of stars of these massive galaxies. And I showed you these three in the earlier plot. And these are the three that we have found that have black hole masses beyond M87. And they're all at distances of about 50 to 100 megaparsecs. So they're much further out, but they are about 3 to 5 times more massive also. So the angular size of the short radius is very comparable to M87. So now, but there are other even bigger core galaxies further out that we're using KCWI to uncover the black hole. And the core sizes we have found correlate with the black hole mass. So by targeting these large core galaxies, we think we are pushing into the even larger black hole regime. And this offers us as a chance to perhaps fill in these, currently there are only a few known beyond M87, and we would like to get the mass function and the number density and so on. So just now I want to move on to the theoretical part. Once we get these extensive data sets, we do have to do a lot of numerical computations to get the black hole mass. So sigma square goes like GM over R roughly, right? But that's really too crude. And we can do a lot better than that. So what we use is so-called short orbit modeling. And that went into the M87's dynamical mass. But here I just want to tie into M87 and show you the 40 years of the mass measurement from stellar dynamical attempts and gas dynamical attempts, and of course the EHT number. So on the surface, the two agree very well, but I just want to stress that the state-of-the-art stellar dynamical measurement of M87's black hole by Gebhardt et al. 2011 assumed an axisymmetric gravitational potential for the galaxy. We have now new data showing that M87 is very unlikely to be axisymmetric. In fact, it shows minor axis rotation. So it's not an oblate axisymmetric system, which you would usually assume that the major axis, right, is rotating around the minor axis. In fact, M87 is doing something quite intricate. So it's really, really important to do triaxial orbit modeling. Okay, and I'll show a couple slides about that. That's what our main effort had been. And we have also obtained a JWST time to observe M87. So a couple words about triaxiality. I think this is very, very important front of dynamical studies right now. As I mentioned, almost all the data points you saw in the M-sigma relation determined from stars made this simplifying assumption. And now through our survey, we are seeing most of these massive galaxies, they're not fast disks rotating about the minor axis. That's sort of a classic 0th order approximation for many galaxies. But in fact, these giant elliptical galaxies, they're slowly rotating, if at all. And whenever we can see some rotation, the kinematic axis is often misaligned from the photometric major axis, meaning it's just not rotating in an axisymmetric way. And this is a telltale sign of a triaxial galaxy. The A and B, C, and the C, the three principal axes, are not of equal length. But it's very difficult to do triaxial orbit modeling because in this, once it's like going from 2D to 3D simulations. Once you relax this assumption, then different stellar orbits are allowed in these potentials. So you really have to compute more stellar orbits in this method. And so we've been working very hard on, and if you are interested in the detail, there are 3 papers you can look at on revamping this sort of first triaxial orbit code by Remco van den Bosch from now some years ago. And this had been applied to only a few galaxies, as I mentioned, in the triaxial setting. And we actually discovered a number of major bugs, which we fixed, and we introduced a lot of improvements. And so we think this code is working pretty well now. Okay, so before I go on to showing you the code, I just want to come back to showing you the misalignment. What do I mean by the kinematic misalignment from the MASSIVE survey? And again, this is just different galaxies, just a bar just to indicate the photometric major axis, which is the black bar for each galaxy. I think this is just oriented north and east this way. Okay, so the bar is the photometric major axis, and the blue-red is from our extensive IFU kinematic data, right? That now we can map out if the galaxy is rotating. If so, what's the axis of rotation? So you can see, I'm just showing you the subsample where the blue and red rotation is not aligned with the major axis of the photometric isophos. Okay, so axisymmetric systems will never exhibit something like this. So it's a strong indication that we need triaxial modeling. Okay, just very quickly, a couple other fronts we are improving to sort of modernize this orbit modeling, which is essential for getting black hole masses out of kinematic studies. The other one is we're speeding up this parameter search space. So in the old days, well, even today, everybody is using brute force grid search in parameter space. Okay, so there, in addition to the black hole mass, which is a parameter in the galaxy model, there's a mass to light ratio for the stars, there's a dark matter halo, and the shapes now, if we want to do triaxiality. So what we do is we assume a static, a Newtonian potential, but we compute hundreds of thousands of stellar orbits to, and then we project on the sky and we find sort of the best fit superposition of these orbits that would reproduce these many, many bins of kinematic information we have. Okay, that's sort of the rough idea of how this orbit model works. So it's a multiple high dimensional search space we have to compute, and each model is very expensive because we have to compute the entire hundreds of thousands of stellar orbits. We have to integrate that. So it's not something very good for MCMC, but we are now, and grid really is impossible when we go to 6 or 7 dimensions here. So we're implementing a much faster Bayesian optimization search way to approach this higher dimensional space, which we need to model the triaxial potential. Okay, and lastly, we're paying a lot of attention to how we compute these higher moments beyond V and sigma. Okay, so just one last slide showing the result is, here is a recent case where we successfully applied our new Trias code to one of the massive galaxies, NGC 1453. It's a fast rotating galaxy, actually, an elliptical galaxy. And just to show you that we can now, in one setting, using this Trias code, we determine the black hole mass, we determine the stellar to mass to light ratio, and sort of 3 shape parameters. So we get the intrinsic 3D shape of the galaxy along with the mass parameters. And this is one of the few cases where you can actually determine the galaxy's intrinsic shape, right? That's a very difficult thing to do, and it requires huge amount of kinematic information, because just photometrically on the sky, you don't know how to deproject that. You cannot uniquely deproject a 2D image, obviously. So you need velocity information. Okay, so yeah, so just one last thing to keep in mind is any black hole mass measurement is only as good as the distance to that galaxy, as we well know. And so for ngEHT also, I mean, it will be useful to think about how will we get distances. And I just want to showcase, so we worried about that for the massive survey at least. So we had in the past 5 years, an HST with PIC3, with C3 campaign using the so-called surface brightness fluctuation method to get distances to these elliptical galaxies. And recently, and because we have the distances that are not just useful for black hole masses, but also for ngEHT, because we have obviously V very well measured. So we actually got a chance to have the largest compilation of SBF distances to determine the ngEHT. So in some ways, we joined the ngEHT controversy, and we very comfortably sit on the 73 side of things. If you're interested, I'd be happy to talk more about it. Okay, so and now I just want to finish with some concluding thoughts. As I've emphasized, direct stellar dynamical black hole mass measurements are difficult, but they're essential for uncovering new black holes because, after all galaxies have stars at the center, but only a select few have masers or CO or millimeter emissions or ionized gas. Okay, and sort of historically, in the 1990s, when the supermassive black hole study became really active, people relied on HST slits. And sort of from the 2010-ish on, we move on to large ground-based telescopes with 2D spectrographs and adaptive optics sometimes to enable us to study these bigger black holes and further black holes at larger distances. So it's sort of a new era now, post-HST era. And as I emphasized, we are working on the triaxial modeling using the Triaxial, which we have developed, and our massive and eMASSIVE efforts into finding new black holes at a high mass end. And here I just want to leave with some thoughts about, the coming decade is exciting, that if ngEHT can become a new way to detect new black holes. And it's been mentioned a couple of times that Dom had this beautiful paper sort of inferring statistically how many sources can be studied, and the numbers, between 5 and 10. But the question now is about where are they? Which systems are we going to look at? And one thing to keep in mind is the two we have right now, they're very different black holes, very different systems. M87 has jet, Gladys Center doesn't. So with the science case, I think the science cases that we're going to talk about this entire week will probably depend on the specific nuclear gas configurations of whatever galaxy we're going to look at. So this is just to leave as a thought for discussion. And hopefully, as we find more black holes, they will provide perhaps candidates for future investigation by ngEHT. Thank you.
Thank you very much, Chung-Pei, for excellent talk. Now we have time for maybe 3 questions. So I can see there is a hand from Shep. He also asked the question in via chat. So Shep, please unmute yourself and ask your question.
For very quickly, Chung-Pei, great talk. In the cartoon you showed of the ladders, for some reason the shadows of the ladders had all broken rungs, and I just wondered why that was, if that's a reason for that. And the second question is, how will JWST affect all of this? Or is there a signal to noise ratio question and it doesn't matter?
Right, so the ladder is just a cartoon, so don't worry about that. It's not meant to be, I just stole it from something, and JW is an interesting question. We struggled with it. The question we worried about was ground-based AO can achieve basically similar angular resolution as JW. So how could we sell a proposal to the TAC? But one key advantage of JW is there are no skylines. And the M87 NIFS data that the dynamical mass is based on is really, really noisy. We have all these lines, skylines we have to deal with in the infrared. And so we're really hoping JW can just provide a much cleaner spectra for us to study. And I think the 30 meter will really be the game changer.
Thanks.
All right, there's a question from Angelo and then from Razi. We have time for 2 more questions. Go ahead, Angelo, and then Razi.
All right. Hi, great talk. I have a question about triaxiality. I'm aware that triaxiality can be invoked to solve the final parsec problem. So do you have a sense if the typical elliptical galaxy is triaxial enough to resolve any final parsec problem?
Possibly. I'm not sure we have done enough triaxial studies, parameter space search, to really quantify how, what triaxiality is needed exactly to solve the final parsec problem.
Okay.
And of course, gas accretion should help, right? So there are many other mechanisms we can invoke to solve the final parsec problem.
Right. Okay. Thank you.
Go ahead.
Yeah, so very great talk. We also have a question regarding to triaxiality. I'm a little bit puzzled. Triaxiality and the shape calculation has something to do with the distribution of the stars, like their location. In my sense, when you compute the shape of galaxy, and I would imagine that whatever shape you actually associate for your star would also depend strongly on the distribution of dark matter. So taking this into account, in many actually different galaxies, we may or may not even have a, very well understanding of distribution of dark matter, how you're going to actually tease it out and just get back to the underlying black hole properties, including their mass. In another word, which one would be more actually dominant source of the matter for the triaxiality of the stars and their shape and so on?
Thank you for the question. Yes. So it depends on the spatial region we probe. And obviously close to the hole dominates gravity. Okay. And then once you go out to about the gravitational sphere of influence, right? By definition, that's where the stars start to dominate. So then for some radial range, stars dominate. And then eventually, of course, you go further out, we go to about a few effective radii of the galaxy. And typically the dark matter starts to take over by, maybe 20, 30%, maybe at most to 50%. So we do model the dark matter. It's more for consistency because some stars do go out, but we don't have a very strong probe of the dark matter. So far we are assuming a spherical dark matter halo, but you're absolutely right. The next order of perturbation would be to allow the dark matter also to be triaxial, right? Or axisymmetric even. But currently it really is the stars' potential. I think that's most important, especially for governing how the stars go towards a black hole. Most of those orbits are very much determined by the triaxiality of the galaxy.
Yeah, that's really great, actually. As a matter of fact, we recently showed using the TNG simulation that the triaxiality of dark matter is very much linked to stars and vice versa. And this is just a step for core dark matter. You could also imagine warm dark matter reacting to other things. And I would imagine that the links between them and then the links to the black hole, I think that will be a little bit more messed up. So that would be fantastic if you great observers can just help us with that. But I was just kind of like confused, how we could probe something, taking this into account all of these, uncertainties and so on. But
right. So I think just the key message is the most of this volume we're probing, the gravitational potential is dominated by black holes and stars. The dark matter, you really have to go further out for it to be that important.
Great. Yeah.
All right. Thank you very much, everybody, for your participation in this plenary session. I would like to also thank very much to the speaker for delivering excellent talk. And I know that there was one more hand raised in chat. I would like to move all the interactions, further interactions into a Slack channel. Okay, thank you everyone for your participations. This session is now closing and we meet in 15 minutes. Thank you very much again.